Hello, my name is Hazik, and today I will be presenting a biomedical signal processing system designed to capture and enhance heart sounds from the stethoscope. This is my circuit. This system processes the acoustic signals by amplifying and filtering them, making the sounds clear and audible through a speaker. Throughout this presentation, I will guide you through the design, operation, and testing of the signal processing circuit, demonstrating each stage step by step to help you fully understand how the system works in a practical setting. Let's dive in. So over here, we are using the TL7072 and we have IC1A over here, which is half of the chip. It is a non-inverting amplifier, so to make it work on a single supply, we're going to use a voltage divider, two 10K resistors, R5 and R6. It gives us 4.5 volts right in the middle of our 9-volt supply, and it goes into the non-inverting output, so the op amp stays centered. Without that, half the waveform gets clipped because the op amp can't go below 0 volts. T3 is a input coupling capacitor. It sits between the microphone and the op amp input. It blocks any DC voltage from the bias microphone, allowing only the AC component, our heartbeat signal, to pass through. TP1 is placed after the coupling capacitor. It gives us access to measure the pure unamplified signal from the mic. Here we got C1 at the input. That's 10 microfarads, which blocks any DC voltage coming from the function generator. C4 on the output side does the same thing. It only makes sure only clean AC signal can pass through. There's a decoupling capacitor which is C2, and it keeps things stable and prevents any supply noise. The gain for this stage is set using two resistors using the formula 1 plus R2 over R3, which gives us a gain of about 23, and it boosts the signal enough without distorting it. As you can see from this table here, the voltage gain of the circuit increases up to 22 volts, which is approximately 26.85 decibels at 100 hertz. After that, the voltage gain gradually decreases, and it is 8.5 at 3K hertz. Also, make sure that there is a 9-volt power supply always going through. TP2 is the test point after this filter stage. On the scope, we will see the 200 Hz waveform passing cleanly, but if we switch to a frequency higher than this, like 1 kHz, it gets noticeably attenuated, confirming that the filter works as intended. Okay, next we got IC1B. It is the second op amp in the DL072 package and is also configured as a non-inverting amplifier. It's just half of the other half of the one we saw in IC1A. But however, this includes an adjustable gain. Alright. R4, as you can see here, acts as the input resistor to stabilize the signal, while R9 and R10 are part of the feedback network. As you can see here, we got a 100 kilo ohm potentiometer P1, which is connected in series to the feedback path. And this allows manual control of the gain using the same formula that we used just now, 1 plus RF over RG. As you can see over here, TP2 is the test point at the output of IC1B, used to observe the amplified signal and confirm gain adjustability. For this test, the channel 1 was connected to TP2 and channel 2 to TP3, which is the output of IC1B. The waveform observed that TP3 had a noticeably higher amplitude than compared to TP2, showing that the signal was further amplified. When adjusting the potentiometer, the output waveform at TP3 changed in size, demonstrating the real-time gain concept. As the gain increased, the waveform showed signs of approaching saturation. However, due to the negative feedback loop in the op-amp configuration, the output remained stable and avoided clipping. So now we have IC2A, which is actually a second TL072 and is configured as a low pass filter. This section is designed to clean up the signal by removing high frequency noise and only allowing lower frequency components like the heartbeat signal, for example, to pass through. Resistors R7 and R8, 22 kilo ohms each, form the feedback network that shapes the filter's frequency response and helps suppress unwanted oscillations. Capacitors C6 and C7 set the filter's cutoff frequency, determining which frequencies get attenuated. C8 over here, C8, is used for power supply decoupling, stabilizing the IC and preventing voltage fluctuations. See here, TP3 here is the test point of the output of IC2A, and we're gonna use TP4 as well for the second probe, and we're gonna use it to observe the filtered signal after noise reduction. Let's go. Okay, so for this test, the function generator was connected as usual to simulate the input signal. Channel 1 of the oscilloscope was connected to TP3 and channel 2 was connected to TP4, which is the output of pin 1 of IC2A. Both waveforms showed similar shapes and amplitudes, but when the potentiometer was adjusted, the signal levels of both TP3 and TP4 changed simultaneously. This is because the potentiometer controls the gain of the second amplification stage, IC2A, and since TP3 and TP4 are part of the same signal path, both are directly affected by gain adjustments. However, in the video that I shared with you, I did not connect channel 1 properly to TP3, and instead I connected to TP1. So uh, in a proper in a correct experiment, there will be proper gain, and as you can see in my video, the output waveform is wrong. Okay, so lastly we have the LM386 audio power amplifier, and it's labeled as IC3, and this is used in the final stage to amplify the signal enough to drive a speaker. The potentiometer P2, just like P1 that we saw earlier, is used to adjust the gain by varying the feedback resistance within the amplifier. C15 over here helps stabilize the amplifier by filtering out high frequency noise and preventing unwanted oscillations. R17 here is a 10 ohm resistor, right? And it works with C15 to isolate the amplifier output and maintain stability by suppressing high frequency interference. C13 over here, right here, is a coupling capacitor placed before the speaker, and it blocks DC and allows only the amplified AC signal to pass through the output, just like the ones previously, and it's the same here. Lastly, TP5 is the final test point, and it's where the speaker signal is measured. The role of this whole stage is to take the already amplified and filtered signal from earlier sections and boost it further to a level that can drive an output device like a speaker. For this test, channel 2 was connected to TP5, which corresponds to pin 5 of the LM386 audio amplifier. The waveform at TP5 showed a much larger amplitude compared to TP4, confirming that the LM386 was providing the final stage of amplification. Adjusting the potentiometer affected the signal at TP5, and you can see after this, and it increased and or decreased, depends on which direction, clockwise or anti-clockwise, you turn it. And yeah, it increases or it decreases the output voltage as needed to properly drive the speaker. This demonstrates the final stage supports higher voltage output, making it suitable for clear audio playback. Overall, the test confirms that the gain control and output response of the LM386 are working as expected.
So